So in this video, we want to go over vector addition now. So we want to start looking at the basic operations that we can do with vectors, just like we can do with numbers or with functions or any other mathematical object we're interested in. I mean, if we can't add them together, then, that would be very limiting in the kind of math that we could do with them, right? So it works in pretty much the way you would expect. So namely, if we have some vector, say, v, which is equal to, I don't know, say 2, 3 in component form. We have another vector w, which is equal to, say, 1, 1 in component form. Then when we add them together, we're just going to add the components together. So their new vector would be 2 plus 1, comma 3 plus 1, which is going to be equal to 3, comma 4. Okay. So if we look at what's happening geometrically, it's a bit interesting here. So if we take the first vector is 2, 3, so it would look like this with initial point at 0, 0 and terminal point at 2, 3. And then we have 1, 1, which is this vector here. So then their sum is at 3, 4. So that would look like this. Okay. So it's a little bit hard to see here, but if we imagined, okay, so if we took this vector 1, 1, and which is w, and we put v on the end of it, what would happen is that we would get to this vector v plus w. So that's what you do, is you kind of connect the vectors together, and then where they end up gives you their sum. Okay. So I guess I'll do it down here, show it a little better here. So if we start with that vector w, and then instead of using the origin as the reference point, if we use this as the initial point of v, so v is at 2, 3. So let's make its initial point 1, 1. Okay, so that would make its terminal point, what color did we use? Black. So that would make its terminal point 1 plus 2, 1 plus 3, which is your vector addition, right? That's what we got over here, 3, 4. So let me draw that out. So that gives us what would be the vector v plus w. Okay. So it kind of makes this like triangle when you put them together. Okay. So just doing it free form here without any graph here. So if we have some vector, say v, and then some vector w here, then the vector v plus w would start at the initial point of the first one and end at the terminal point of the second one. Okay, so this would be v plus w. So that's what's happening geometrically, but of course algebraically it's just as easy as adding the components together. And subtracting will work the exact same way. If you have, if we just use the same ones that we had here, actually, v and w, if we do v minus w, then this is going to be 1, comma 2. So we just subtract the components. And that's because this is really just like adding v plus -1 times w. And we're going to talk about multiplication like this, but essentially all this is going to do is it's going to reverse the direction of the vector. So geometrically to work out the same way is just subtracting the components. Okay. So yeah, so there's not a lot to it here. We just basically add them together. or we subtract them together and we do it component wise. And we're going to see that's kind of how a lot of these vectors work, is that we'll be able to just do everything component wise. Yeah, I mean, and there will be some cases where we can't, but in general, it will be that easy. I do want to use this as an opportunity just to talk about some of the other ways that we refer to vectors. So I mentioned, specifically in statistics, we'll have a vector of data, say x, and x will be equal to x1, comma x2, all the way to xn. Okay, so this is one way we can refer to vectors, just with the parentheses like this. Specifically, when it's horizontal like this, we might call it a row vector. And you might use brackets instead. That's fine. Brackets and parentheses are pretty much used interchangeably with row vectors. Oftentimes, we also might represent it as a column. Okay, and then in this case, it's called a column vector. And this is pretty common too. I believe this is the default in R. By default, the programming language R, just if you've used it before, it'll try to make the dimensions match automatically. But otherwise, I think it defaults to a column vector. So, using it in this form, we see that vectors are really just kind of matrices. They're very similar to matrices because they are matrices. Like this one is in a 1 by n matrix, and this one is a n by 1 matrix. So vectors, so if you're already familiar with matrices, then a lot of this will kind of be familiar. If you're not, that's fine. I just want to kind of relate it to something you might have already seen before. Matrices, of course, are used in statistics all the time, in statistical theory at least, just because, a table of data is a matrix. So they're very convenient. So something like this would maybe in statistics be more commonly represented like this, or maybe like this or something like that. So these would all be different ways to represent the same thing. And it would just change between column or row vectors depending on what your dimensions are, because you might need a row or a column vector if you're doing matrix multiplication because you need the dimensions to match. Other than that, there's really not a lot of difference. You just, tweak everything to, fit the way that you're doing it. Another thing I wanted to mention is this arrow over the V, which I said type this will be bold. Another common thing is to put a hat over it. I think we like to avoid that in statistics because we use hat for a different purpose, which is we use the hat when it's something that's being used to estimate a parameter, right? So we kind of use it as like an estimation instead. So we don't really use it for this purpose, but I know in like engineering and stuff, it's very common to use hat for vectors. So that's something to keep in mind as well. So we talked about addition and then just a little bit about the different ways we can represent vectors. Now that we're kind of seeing, I wanted to mention it here because, if you know matrix addition, this is exactly how matrix addition works as well, right? When you add two matrices together, you just add the components together, right? So now I want to talk about the different types of multiplication. So first we're going to talk about scalar multiplication. Okay. And we first need to define what is a scalar. Okay. So a scalar is in this context, is a real number. Okay. So vectors are different from real numbers, right? Real numbers are numbers. They represent a quantity of something. Whereas a vector is giving you a magnitude, which is a quantity, and then also a direction. So they're a little bit different. They have more of a geometric meaning than a real number does. But we can mix the two. Okay, so we can take a real number and we can multiply it by a vector. So for example, if say we have the vector v and it's equal to, let's just say 1, 1 first. Okay, then what do we expect 2v to look like? Well, just from what we know about multiplication and we know about vectors, you know, this is a vector with a certain magnitude, right? So it goes out to 1, 1, and it has this length here. So we would expect 2 times this to have twice the magnitude. So in other words, we would just double the length of it, and it would look something more like this, right? And that's exactly what we want this to look like. So geometrically, what this means is that we're just going to multiply each component by 2. Okay. So this is just going to equal to 2, 2. So with scalar multiplication, we can kind of move scalars in and out of vectors as we please. So it's sort of like the distributive property, you know, where we can move between multiplication and addition. Same kind of idea here, where we can move with real numbers and vectors back and forth between them. So likewise, this means that if we have some vector w, which is equal to, say, 4, 6, we can rewrite this. We can write 4, 6 as 2 times 2, 3, right? And then say 2, 3, that's what we had for w before. So maybe let's make this one u, and then use the same thing for w that we had before. Then this would be equal to 2w. Okay, so we see that u is equal to 2w. So not only can we bring a real number inside for the scalar multiplication, but we can also factor one out. So we can move both ways with it. So we can take a scalar, which is just another name for a real number, just used in the context of vectors here. And we can multiply each component by the scalar. Again, relating it to matrices. You know, if you're not familiar with matrices, you can kind of just ignore this part, but I just want to do it just in case you are, because it might help some things click better. If you take a matrix and you multiply it by a scalar, you do the same thing, right? You multiply each component by that scalar, and that gives you your new matrix. So it works the exact same way as matrices, as we would expect, because vectors are matrices. So one thing we cannot do is that we cannot add a vector and scalar. Okay, so this does not make any sense, right? So if we have some vector v, which say is 1, 1, we cannot do v plus 2, for example. This doesn't make any sense. In the same way that it wouldn't make any sense for matrices. If you want to add matrices together, they need to have the same dimensions. Same idea with vectors. They need to have the same dimensions. You need to have the same number of components, right? This is like saying we're going to take 1, 1 and add 2 to it. Well, where do you put the 2, right? Do you put it with the first component? Do you put it with the second component? And if you decide, well, I'm going to put it with the first component, now you open yourself up to having non-unique answers. So it's not a well-defined operation. So it's just something that's not allowed. Okay, so this does not make any sense. Okay, so we can multiply by a scalar. We can add two vectors together or subtract them, but we cannot add a scalar and a vector.